Or to this computer. Okay. So I think recording is in progress. Yes. All right. So let's close this. No, 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 no. This is not what I want. All right. Let's just hide this away here. And okay. So let's begin. Before we begin, do we want to talk about anything that was left behind from last class on OpenMP? Do you guys feel okay with that? Is there anything you'd like to discuss or anything you'd like to talk about before we go on? Okay, I can give you guys a little refresher on important things you should remember. We're gonna, oops, no. We, where are my slides? Why is everything so difficult? Okay. Right, so these lights are on Steve's, course page. You guys can get to it later if you want, but a little bit of a refresher. So OpenMP is a particular way of doing shared memory parallelism, right? Shared memory parallelism is the type of parallelism you guys have been talking about so far, is the one where you have a process. Each process has threads, and those threads have a shared memory pool that they can read and write from. And of course, this presents problems. You have to be careful when you read and write to memory, right? You have to coordinate your access to threads. And like I said, OpenMP is one particular way of doing that, right? That people came up in the 90s. It's very popular in the HPC community, right? It's intended to be used with C, C++, and Fortran. And the way that it works is it extends your compiler, right? And it extends your compiler by giving it some pragma directives, right? And a runtime library. And the way that it does parallelism is the fork join model. So you have one main thread, that thread spawns a team, you do parallel work, you join at the end, right? Some important concepts and important constructs here that we talked about is pragma ONP parallel. This one is the one that creates a team of threads and executes the block of code in parallel. Each thread executes the same code, remember that, right? And the way that you differentiate between threads in a team is you call these library functions. So get thread num gets you the total number of threads. Sorry, yeah, I'm always confusing these two. So get thread num gets you the thread ID, right? So the ID of this thread in the team of threads, and get num threads gives you the total number of threads, right? We can request a certain number of threads either by using environment variables, so open OMP num threads, or we can call OMP set num threads in from the code directly, right? We have these two important synchronization primitives, right? So remember that, does everybody remember what's the difference between a barrier and a critical section? That's exactly it, right? A barrier is a synchronization point. You stop at the barrier. Every thread reaches the barrier, and then after that, they continue. A critical is a mutual exclusion, right? Only one thread will execute the critical section at a time. Remember that we had, that thing that was an accumulator. We used the critical section to write to that, right? We also discussed OMP parallel 4, right? Remember that we had the example where we've partitioned the work manually. You can do the same thing by calling OMP parallel for. You don't have to partition anything manually. You just have a regular for loop. You just stick the pragma before the for loop, and it will be automatically parallelized by OpenMP. Now, it's important to remember that your loop iterations still need to be independent of each other, right? If for some reason, your loop iterations are not independent, OpenMP is not going to fix that problem for you, right? So for instance, with the accumulator problem we had, right, we still have to think about the fact that we want to have a variable that's shared across the threads, and we still have to take care of that. So what parallel for does is it takes care of the distribution, but it doesn't automatically prevent you from getting into data races and problems. Okay? And the last bit that I think we should probably talk about is the reduction operation, right? So suppose that we have a situation like this, like I was telling you, we have an accumulator, right? So in this situation, we want to compute an average, right? We have an array, and we want to store the average of the values in the array into this AVG variable, right? If we do that in serial, what we do is we do a for loop, right? We loop over the array, and we add the values in the array to average, and then we divide it by the size of the array, and then we get an average, right? So how can we deal with that sort of situation if we use OpenMP, right? We can, like I said, we can just stick the pragma ONP parallel for, right? Before for a loop. So the loop ranges, the loop body, nothing changes, right? But because we have a carry dependency, right? Because every thread then is going to want to write to this AVG variable, we use the reduction operation, right? And remember, what reduction does is basically it says that this variable called AVG will have a local copy on each thread. And at the end of the parallel work, the operation that's specified here will be applied to each local copy of the variables, right? So every thread will have a copy of AVG and will write, will add to its local copy the value of AI. And then when this loop ends at the implied barrier here at the end, right, all of these local AVGs will be combined with a summation. And then we have, the total sum of each of the parallel workers. And then we can just divide them on and so on. Okay? Yes.
I still don't quite understand what a reduction does.
Okay. So a reduction is an operation in a variable. Okay? So what the reduction is going to do is it's going to apply the operation you specified into a certain variable, right? So what we're doing here in this case is that we have an average variable, right? And this for loop is running in parallel. So we can imagine, so let's think that we have two threads, right? And or three threads, right? And all of them, right, will be reading at different values of this array, right? So thread 1 will read, say, value 0, thread 1 will read value 1, and thread 2 will read value 2, right? All of these threads, they want to add their partial values, their partial sums into this average variable. But they can't do that without care, right? So options for doing that. We've seen one of them. Using a critical section is one of the options we have, right? Or, using an array of sums and adding the sums to an array, it's another option, right? The reduction operation is going to be similar to the array solution, right? So what this is telling OpenMP is the following. Okay, I have this average variable AVG, but I want every worker in this for loop to have a copy of this variable, a local copy of this variable. Okay, even though it's supposed to be shared, I want every thread to have a copy of it, right? And after you're done with your parallel work, I want you to apply an operation to combine each local copy that each thread has of this variable using that operation, right? So in this case, we're saying that the operation is sum. So each thread has a local copy of AVG. And when OpenMP finishes the for loop, it's going to ask for each thread to give it its local copy of AVG, and it's going to sum those copies for us. Okay? So the result that we're going to observe here in the end is as if, we had specifically declared local copies and then added them at the end to AVG. Is that more clear? Right? So this is what you have to think about. So a reduction, it will distribute the variable across the threads and will combine the local values using the operation you specified. We've only talked about some, but you could do other things. There's a whole lot of operations you could do. You could do logical combinations, you could do subtractions, you could do products, right? Well, we're not going to worry about that. Yes.
Do all the reductions correspond to the operators?
So there's a little table of operators that you could use for the reduction call. You should probably not worry about that too much. This is more informational, just so that you know what you can do, right? But so if you don't want, like, and all of them have an initial value, right? So, you can do a min, you can do a max, you can do logical operations and things like that. All right? Great. Any more questions on OpenMP before we move on?
Near the end of class yesterday, we looked at that graph of Amdahl's law, and
The-
there was that.
The dip?
Yeah, the dip.
Right. So you have a question about the dip, or you have a theory about the dip?
Curious to see what it actually is. I don't have that theory.
Well, that's sort of for you guys to try and figure out before I give you the answer. I want you to think about why that's happening. And if possible, it would be cool if you guys could run some local experiments to see if you observe that on your machines, right? All right. So today I want to briefly talk about, before we move on to other topics, I want to talk about MPI. And MPI is a different way of doing parallelism, and it's different than what you've probably been used to, and different than anything you've done so far, I'd wager, right? Because MPI, the fundamental distinction between the MPI way of doing things and the OpenMP way of doing things, right, is that MPI is a distributed memory parallelism paradigm, right? So this is a repeat of the slide that we had for OpenMP, right? So usually you have a process. The process has a number of threads that it can spawn privately, and it has some private memory that it can access, right? And, if you go over these ranges, right? If you go over these ranges, you get a segmentation fault. The operating system doesn't like that. It'll kill your program, right? And shared memory parallelism is about coordinating these two threads to access this memory in a well-behaved and controlled fashion, right? And that's now, in contrast to that, right, we have shared distributed memory parallelism, okay? So the concept here is that, okay, let's say that instead of having a single process, I have more than one process. And each of these processes, from the operating system point of view, right, they're going to have their private data, their private threads, everything as normal, right? But let's suppose that somehow we can make it so that these two independent processes communicate in some sense, right? And by communicating with each other, we can achieve it to complete a task in parallel, right? So the paradigm that implements this sort of this sort of thing is the message passing paradigm, right? So there is an important consequence that I said here in the slides, right? But I'd like you guys to think about it, right? I am saying that under this paradigm of parallelism, right, if you do everything correctly, and if you do, like in normal scenarios, you don't have data races, right? You eliminate the problem of data races. Would you guys be willing to try to explain why that is? Right. Let's think about it. Yeah, you have a
So since it's distributed and there's no shared memory because the processes themselves are allocated different memory by the OS.
exactly, right? So you have two different processes. These processes have their private memory spaces that neither of them can access, right? So you don't get data races because you don't have the situation in which the two processes are trying to write or read across their memory boundaries because the OS doesn't allow that, right? You're not supposed to be doing that, right? So it's through this independency, right, that you achieve safety from data races, right? And this model of doing things is different than what you're used to because you have to be explicit about the communication now of these two processes, right? One process needs to send a message to the other process, and the other process needs to respond back with a message, right? So it's all about explicit communication patterns between processes that will coordinate to do parallel work. Okay? So I really like message passing. I think message passing is great. And I think it's superior to the threading model, right? But it is not as common as shared memory parallelism, right? For multiple reasons, but we'll be talking about those reasons, I think, soon, right? And so what's MPI specifically, right? So when we're talking about OpenMP and we're talking about threads, I told you guys that most programming languages these days have a way to spawn threads and run threads and do things using threads and shared memory parallelism, right? The situation is different if you want to do distributed memory parallelism. So most programming languages don't have any kind of facility to doing that, right? Two exceptions that I know of are Julia and Fortran, right? They have a facility that allows you to do remote execution. So in Julia, for instance, you can say, okay, I want you to spawn this code and I want you to run this code on a different computer on the network, and then I want you to give me a future to the result of this code and then that I can look up on in the future, right? Things like that. So MPI is still the king of specifications when it comes to distributed memory parallelism, right? And the story of MPI is closely related to the story of OpenMP. It began in the 90s because there was, a vendor hell, right? So in the HPC community, uh, you build supercomputing clusters by stacking a lot of compute units, and then you replicate that across different nodes and you interconnect them with an Ethernet connection, right? That's how you get a supercomputer. And you need some way to do remote communication with these different nodes in these HPC machines, right? And there were different standards, and every different vendor wanted to use something different, right? Until in 94, people came together and created the MPI standard, right? And MPI stands for the Message Passing Interface. So again, it's a big book of rules, it's a specification. It tells you what you need to do and defines what a message is and how do you communicate with other processes and how do you pass messages, what do you expect when you pass messages around, and so on, right? And MPI is very, very relevant even today, right? So you probably heard about the top 500 list, right? So the top 500 is the list of the 500 fastest supercomputers in the world, right? And all of these supercomputers, regardless of what they're doing for their compute units, whether or not they're using CPUs, GPUs, or other kind of accelerators for their computations, they're all using MPI for their interprocess and internode communication, right? And these days, MPI can even be used to communicate with different GPUs across different nodes, right? You can send memory from one GPU or one compute device to another compute device in a different node, and it just works, right? So MPI is still super important and it's super relevant. And if you go into HPC, you're surely going to have to deal with it at some point, right? And, the latest release is 2025, June 2025, so kind of recent, right? We have three major implementations of the MPI standard. OpenMPI, which is, an open source. Well, these two are open source, right? OpenMPI and MPitch These two are open source. MPitch is done by the Argonne National Laboratory. OpenMPI, I'm not sure that's backed by any laboratory. And Intel MPI is backed by Intel, right? And so when you install MPI on your machine, it's a library, right? You're going to be installing one of these three different implementations, right, of MPI. And you're going to be using that runtime library to do your parallelism. Okay? So do you have any questions so far? Any comments? Anything you'd like to? All right. So the most fundamental thing you have to remember about MPI is that it uses the SPMD paradigm of parallelism, right? And that stands for single program, multiple data, right? And what that means is that MPI programs are executed via compile and executed using certain wrappers, right? So if you're using C and C++, you're going to use MPI-CC or MPI-C++. And if you're using Fortran, you're going to use MPI-Fort. And they're going to be executed also with a launcher program, right? Which is called MPI exec, right? And in this case, MPI exec is going to launch 4 versions of your program called hello. Okay. And this is the important bit. What the SPMD model says is that the 4 versions of these program will be identical, right? So you're going to launch hello 4 times, and your operating system will see 4 independent processes running. Okay. They were all created though via MPI exec. What makes them special is that these 4 programs can communicate with each other, right? And they can communicate with each other by calling certain instructions in the source code. So in your source code, you're going to have a little bit of code that differentiates what you're going to do based on the process ID that you get when you run it. Okay? That's similar to what we were seeing with OpenMP, right? When you launch a group of threads with OpenMP, every thread executes the same block, you differentiate by an ID and so on, right? Is that clear? Does everybody understand that? Okay. So what do we mean by, all right. So a few more fundamental concepts that we have to think about. MPI processes are arranged in data structures that they call groups, right? And groups can have multiple what they call colors, right? So a color is just a little bit of extra context, right? When you combine, a group of processes and some bit of extra context, you get a communicator, right? So a communicator is like, you can think of a communicator as a sort of a group of processes that will participate in some communication and that can all talk to each other, right? So let's say that you spawn, for instance, 4 processes, right? You can combine these processes in different communicators, right? You can combine 2 processes in one communicator, and then these 2 can talk to each other. And then you can combine the other 2 in another communicator, so those 2 can talk to each other. Or you can combine them like this, right? These 2 in the middle can talk to each other, and these 2 in the edges can talk to each other, right? So communicators can be made to overlap, and they can be made to intersect, and they can be all sorts of complicated structures that you can create with communicators. And when you send and receive a message, you always do it in a communicator, right? So you do the messaging with the processes that are part of a certain communicator. And there is one communicator, which is global, and it's always available to you, right? Which is called MPI-COM world, right? MPI-COM world is the communicator that has all of the processes that have been launched by MPI. Okay, the global communicator, the communicator that contains them all, right? And when we have a process in a communicator, right, this is a little bit of a technical detail, but we don't refer to it as a process because remember, the same process can be part of different communicators, right? But a process in a communicator gets a name, right? And it's called a rank. And by using the rank number is how we identify who we are talking to in a certain communicator. Okay, so this example, this diagram here, tries to illustrate this concept, right? So here we have 8 processes. Sorry, we have 16 processes, right? So from the operating system point of view, the 16 processes were launched via MPI exec, right? And we have always one communicator, which is MPI com world, which is the big green shape here, right? It's the communicator that envelops all of the processes. And you can see here that we have 3 numbers, right? So the numbers in the outside are the ranks as viewed by the global communicator, right? So if you're using the green communicator to do message passing, right, and you want to talk to this process, you would call it rank number 10. Okay? Now, we can have different communicators that are subsections of this global communicator, right? We can have, for instance, this red one, right? This red communicator involves only these processes, right? So from the point of view of the red communicator, this is process 0, and this is process 1, and this is 2, 3, 4, 5, 6, and 7. But from the point of view of the global communicator, this is still 1, 2, 5, 6, 9, 10, so on and so forth, right? And something similar happens with the blue communicator. Okay? Do you have any questions? Are things making sense so far? Okay. Do let me know if I'm moving too fast or too slowly. So there are many ways of doing communication using MPI. We are only going to see one, and it's the most basic one, right? Which is called point-to-point communication. Point-to-point communication, as the name implies, is you have one process, you directly send a message to the other process, which directly receives it, right? You have 2 participating processes in point-to-point communication. You have an origin point and a vanishing point. And this is very important, right? In point-to-point communication, both the sender and the receiver process have to do something, okay? So API-wise, if you are the process sending a message, you're going to call MPI send, right? And if you're the process receiving a message, you're going to call MPI receive. But remember, so you wrote your program, you have a single source code, right? That is driving the behavior of these 2 processes. Still, they need to have different behavior, because if you have 2 processes and one wants to send and the other one wants to receive, you have to have an if statement somewhere that says, okay, if I am process 0, I want to send. Else, if I'm process 1, I want to receive, right? And you have to explicitly call send in one and receive in the other. Because what happens if you don't do that, right? Does anybody have a guess? One process wants to send a message, but the other process didn't post the fact that they want to receive a message. So these functions are blocking, right? So you guys have any idea of what's going to happen?
Synchronizing?
It's not.
Ah,
It's not. What's going to happen is that your program is going to deadlock, right? And because one of your participating processes wants to send a message, but there's no one else to receive it. And this is a blocking call, which means it only returns when the communication has completed, right? And so because this only returns when the communication has completed, but there is no one to receive the message, the communication will never complete. So you're going to deadlock. Your process, your sending process is going to spin forever, right? The same thing can happen if you have a receive and no send, right? If you're a process and you're saying, okay, I want to receive a message, but nobody send a message to you, you're going to sit there waiting, doing nothing until a message comes. But if a message never comes, you're going to wait forever, right? So these calls, MPI send and MPI receive, are what it's called blocking calls, right? And synchronous communication, right? They do have advantages though, right? So the message you're sending is actually memory, right? So when you send, what you're sending is actually a sequence of bytes, right, to the other process. So because you're sending a sequence of bytes and you're receiving a sequence of bytes, first you need, like a source, sequence of bytes. It can be a variable. It can be something that you've allocated dynamically, right? And you also need a place to put those receiving bytes, right? So when you're doing the send and receive operation, these send and receive memory buffers, right? They might be in an indeterminate state, right? You don't want to mess with them while communication is happening. You don't want to overwrite the send buffer, right? And at the same time, you want the receive buffer not to be written by someone else. So these blocking calls, they guarantee that if they return, the communication is over, and the buffers that you're using to send the message and to receive the messenger are now safe to be reused, read, written. You can do whatever you want, right? Because this implies a synchronization. I send a message, the other process receives a message, and it's guaranteed, if these functions return, that the buffers are filled with data and we can proceed. All right? Do you have any questions so far? Okay. There's a typo here. Now, what do you think these functions do, right? Non-blocking point-to-point communication. What do you think these are about, based on what I just said? Right? Yes,
They don't.
they don't deadlock, but why? Yes, exactly, right? So MPI I send and I receive, they're going to do exactly the same kind of thing. They're going to send a count of bytes to another process, which is going to receive that same count of bytes and put that into a buffer of its own, right? The difference is that they return immediately, right? So you call these functions and they return, right? What happens is, and the vocabulary around this is that they post a send request and that they post a receive request, right? So it's as if one of the processes raises a flag and say, hey, I want to send data. Whoever wants my data, I'm ready to send, right? And it's looking at the buffer and it's saying, okay, I want to send that buffer, right? Please don't touch that buffer. I want to send it in the future soon, right? And it waits until somebody else in the other side of the room raises the flag and says, hey, I want to receive the data and I want to put it here, right? So when I see that the other process is ready to receive, I get my data, I give them my data, and we put our flags down. And then communication is over, right? And then after that happens, the buffers are safe to be reused. But because these functions return immediately when you call them, right, you need some sort of way to know in the future, after you gave the send and receive instructions, you need to know if the communication has completed or not in the future, right? And that's why after you call MPI I send or MPI I receive, you're going to have to call an MPI wait function, right? And what these functions give you is that they give you some sort of handle. Have you guys ever heard about the concept of futures in certain programming languages? Right? Yeah, you go ahead.
Okay, I was just checking to see if there's like a promise.
Yes, it's like a promise, right? So what happens is you'll get a handle to some object, right? And you can query that object to know if the operation has completed or not, right? So you give the computer an instruction, which will be performed at some point in time in the future. You don't know when, right? The way that you know when is that you use this object, this future, or this reference that it gives you, right? And you query that object and you say, okay, is this thing here ready, right? Is this operation completed? And this is what these functions do. They give you a handle to something that you can wait on in the future, right? So is everything clear so far? Any questions? Okay. So doing this avoids deadlocking, right? Because you're just posting sends and receives and you're continuing immediately, right? Of course, if you don't wait, other kinds of problems can happen, right? While this communication hasn't been, done, you expect that nobody will touch and mess around with the buffers that you want to send and receive, okay? And this also opens up a very interesting possibility. The possibility of overlapping computation and communication, right? Can you guys see why is that true? Yes?
Because you can post that you want to send something and then somebody can modify the buffer and then the person who receives it gets really random computation.
Well, yes, that's a problem, but that's not exactly what you're talking about. Overlapping communication and computation can be a good thing if you know how to use it. You wanted to say something, yes.
Uh,
Yes. Yes, exactly, right? So that's the idea. Let's suppose that I want to do some work. Part of my work depends on knowing information from you guys. But part of my work is completely known to me, right? So what I can do is I can send you guys a text message. Hey, can you please tell me that number, right? And while I wait for your text message to arrive on my phone, I do something else, right? So we are overlapping computation and communication, right? And that is a good thing. If you know how to harvest this, this is how you extract performance out of your parallel programs. One of the ways, at least, right? So for instance, if you're doing some very expensive file IO operation, which is expensive because you have hard drives, you have to spin the disk and you have to search the data, you can just send some sort of, spawn a communication, right? Spawn a subprocess that does that. And while that's being done, you're already doing something else, right? While you're waiting for the IO to complete. Okay? All right. So I think we're ready to see some examples. Otherwise, it's going to be too late. Well, okay. I just want to mention that there's different things that we can do, right? Apart from point-to-point communication. There are these things which we'll not cover, which are called collective communications, right? And this is based, so reduction, you guys know what a reduction is now, right? All of my processes have a value. I ask, and I so say that I'm the root processes and you guys are the worker processes, right? And each of you is doing a part of a computation. And I ask all of you, hey, I want the result of your computation and we'll combine them all in onto me, right? This is a reduction operation. Every process sends me something and I combine them using an operation, like an OpenMP. A barrier is exactly what happens in OpenMP, right? Every process needs to reach that point before proceeding, right? So we're exiting through the door. We all have to get through the door before we proceed, right? And there's also the concept of broadcasting, which is kind of the inverse of a reduction, right? In a broadcast, if I'm the root process, I'm going to give each and every one of you some data, right? And you're all going to receive it. So instead of having to call, send, receive, send, receive, send, receive, with each and every one of you, I can just broadcast, right? The thing that I want to broadcast. There's much more, right? MPI is very complicated. There is a lot of functionality. We won't see a fraction of it all. We're just going to focus on sends and receives. Okay? And the motivating example for today is Conway's Game of Life. Did you guys probably heard about this one before, right? Yeah. Heard about it? Okay, so Conway's Game of Life is a 0-player game in which you have a grid, right, of cells. And each cell can be either alive or dead, right? And if a cell is alive, you color it with a color. And if it's dead, you color it with another color, right? And you can have a certain number of generations in this grid-like block thing, right? And every generation, you decide if a cell is alive or not by applying certain rules, right? And these are the rules. So if the cell is alive and each cell is going to look at its 8 neighbors and it's going to decide what's going to be its value in the next iteration, if it's going to be alive or dead, right? So, the game is played by, okay, you choose a number of iterations, a number of steps, and then you loop through each cell and you apply these simple rules, right? In which everyone looks at their neighbors and decides whether or not they are alive or dead. Okay? It's a pretty simple thing, right? So, okay, how do we parallelize this sort of thing using OpenMPI, right? So let's focus on the diagram on the left first, right? Let's forget about all the rest, okay? This is the board of Conway's Game of Life game, right? We got the cells, right? And each of these cells can be alive or dead. And to determine, so let's say that I'm analyzing the cell here in grayish color, right? And I want to decide if this cell for the next iteration is going to be either alive or dead to know the color associated with it. I want to apply, so I apply those rules, but in order to apply those rules, I have to look at all of my 8 neighbors, right? Okay. So let's suppose then, right, that we're going to split this board now, right? We're not going to do it serially. We're going to do it using MPI. And we're going to split the rows horizontally, right? We're going to split this board horizontally, and we're going to give one process a portion of these rows, and another process a portion of these rows, right? Okay. Now, the problem is the same. We're going to walk through each of these cells, looking at my neighbors, right, and deciding if I'm alive or not, okay? But let's consider what happens here, okay? Let's suppose that I'm trying to decide if this cell is alive or not, right? I need to look at my neighbors. But the problem is my process, right, only has part of the grid. I don't have the whole of the information that I need to decide whether or not I'm alive or not, right? Can you see that? Right, I have the information down here, but I don't have these guys, right? So how can I solve this problem? Do you guys have any idea? Guesses? I should have hit this because this gives it away, but pretend you're not seeing this. Yeah,
Just make them communicate their data on the edges, I guess.
on the edges. Oh, I see. On these edges. Well, that is an option, right? But can you see a problem with that? That's not going to be wrong. The result is going to be correct, right? So what you're saying is, okay, so if I am this cell and I want to know this value, I ask this guy, hey, can you please give me the number that you have in there, right? Can you communicate like this, right? And so you fill this number by asking the red grid this question, right? That is one possibility. But can you see a problem with this approach? Yes. Not necessarily, because you could use asynchronous communication, right? Well, I mean, of course, you're going to have to wait for a response regardless, but can you try reformulating what you're trying to say? Maybe you're trying to say the right thing, and I just didn't pick it up.
Because, it's when your process on your grid need access to another process. Then, you have to send a request. but
Yes.
You still have to wait for it to respond.
Yes.
Well,
Yes, exactly. Well, you're going to have to do that regardless, right? Like we know that some communication will have to happen. But what you're saying is that it's inefficient to do that like this, right? So a single cell asks for the information of a single cell, I guess, right? That's what you're trying to say? Yes.
So I guess, like the edges could be like buffers,
Ah,
so that, because we delegated processes to regions, but we kind of have that, but we still have double counts. So it's a complicated one.
here's the thing, right? Why isn't it? Well, okay, so it works if I just do single communication. So I am this cell, I need this information above me. So what's the most direct way of obtaining it? I ask the red grid to give it to me, right? And for each and every one of those cells here in the blue grid, I ask the same question. But let's suppose for a moment that I am one of these neighbors, right? If I am this guy, I still need the information that comes from here, right? Can you see that? Because when I slide this thing to the right, this, I'm going to need the information of this cell in this step, but I'm also going to need the information of this cell in the next neighbor that I'm querying. So I'm going to ask for the same information multiple times if I do it like that, right? So if I do one-to-one for every grid cell, if I ask the other grid, hey, can you give me the value? Hey, can you give me the value? Hey, I'm going to do the same operation over and over and over again. And the result is not going to change, right? So there is a smarter way of doing this. And the smarter way of doing this is like kind of like you said, but people don't call them buffers. They call them halo exchanges, right? Why is it a halo? Well, okay, so we have a grid, right? The red grid, exactly the same red grid. And we're going to extend this grid, right? We're going to extend this with 2 rows, right? Which we call the halo exchange zones or the buffer zones or the ghost zones, right? There are many names for this concept, but we're going to enhance this grid with these 2 extra rows, right? And instead of asking the question every single time, what we're going to do is we're going to communicate it only once, okay? So if I'm the top grid and I want to fill this bottom halo zone, what I'm going to say is I'm going to say, okay, blue grid, I want to fill this information with all the values you have in your first row. Okay? So the arrows here are indicating that the information from this row is getting copied over to here. Okay? Can you see that happening? Right? Something similar is going to happen with this one, right? Oh, the blue grid is going to say, okay, red grid, I am going to fill this halo zone with your last row. So the last row of the red zone is going to be copied over here. Okay? So each of these guys is going to have a little bit of information from the other one, right? But if you do it this way, you can exchange the entire rows with a single communication, right? The row exchange bit, you can exchange the entire row, and you don't have to exchange individual cells every time. So it's more efficient for each process to store a little bit more of memory and communicate less than communicate more and store less memory, right? And so this is how we can solve this problem, right? Adding these halo zones, we get the information we need. Any questions so far? Okay. You want to say something? Okay, it's fine. All right. So let's look at some code. And let's go straight to the Game of Life source code. Okay. All right. So every MPI program will begin by including MPI.h, right? This is a purely runtime library. This is what's going to give you access to, this is what's going to give you access to all of the MPI function calls that you might want to have. All right. So MPI has needs for you to call MPI init and MPI finalize, right? So MPI init is the function that signals to MPI that you're going to be using MPI to do communication with this process, right? And then at the end of your program, if you go down to the bottom, you have to call MPI finalize. I don't know if you guys have used like old-timey C libraries, right? But usually old-timey C libraries are always like that, right? They have some initialization functions and finalization function, and MPI is exactly like that, right? And another thing that MPI wants is it also wants the command line arguments that you may or may not have passed to it because it does stuff with that, right? Okay, so here we have two calls that you're going to see in almost every MPI program. I wish to say all of them, right? Which is MPI com rank and MPI com size, right? Again, this is an old-timey C library. So the way that you do this is it doesn't return values. You give it buffers, and it fills the buffer with the value. So com rank, it's going to give you the rank of this process in this communicator. We're only going to use the global communicator for this example, right? I'm not going to use subcommunicators. Com size gives you the size of the communicator, the number of processes you have, right? So this is me just, I'm going to control this thing with a TOML file, which will pass on, right? This is not important, but here's something that may or may not be interesting, right? I have defined this thing called root print line. And this is a macro. And what this does is it only prints if I am process 0, right? Because if I don't have this, every process is going to try to print the same thing to the screen, and you're going to start seeing repeated messages, right? So process 0 is going to print something. Process 1 is going to print the same something. You're going to get a stack of messages in your terminal, right? So this sort of guards you from that. Okay. Now we do this, right? Compute partition. So given a grid size, we want to know how many rows each process is going to get. And the way that we do this, the math that we do this is exactly the same math that we used in the OpenMP example, right? Where we compute the rank, we give each process as many rows as we possibly can. If they're not exactly divisible, one of them are going to be a bit lopsided, right? But that's exactly the same logic. It's just a copy and paste of that, right? Okay. So this is just guarding against the possibility that some of the processes might be idle, right? Depending on your configuration. So if your grid is smaller than the number of processes, right? Some of the processes are going to be idle. So what I'm saying here is, okay, if you're a process and you're idle, just quit, right? Don't do anything, right? So this is where we allocate the buffers, right? So these guys are going to hold the partial versions of our grid. Remember, each process has a piece of the grid, right? So this is where we are allocating these pieces, right? And we're also giving them 2 extra halo zones, which are going to be using for the sends and receives. Okay? All right. So this code is about initializing or grid. I have allowed this to be initialized with 2 types of initial conditions. You either just write a bunch of random values to the grid, or you just write this thing which is called a glider, right? Which is one of the constructs in Conway's Game of Life that moves around, right? So here we are getting who our neighbors are, right? So I want to know what's the rank, what's the ID of the grid that's above me, and what's the ID of the grid that's below me, right? In order to do the communications I need. And this is where I do the magical communication, right? I say that I want to receive 2 rows of data, right? And I say that I want to receive 1 row of data from the process above me and 1 row of data from the process below me. And I also want to send my data to another processes, to 2 other processes, right? So I post my receives and I post my sends. And these are asynchronous. They're going to happen sometime in the future. This MPI request thing here is capturing those futures, and I have a call to MPI wait all, right, to make sure that this communication has completed by this point, right? So at this point, I have all the data that I need. All I need to do is I need to loop over my local grid, and I need to apply, Commons game of life rules, and that's all, right? And that's what I'm doing here. I'm just looping over the rows, looping over the columns. I apply, these are the Conway's game of life rules, okay, if I have X live neighbors, unalive the cell, or things like that, right? And this is just a diagnostics, right? So at every step, we're going to see if we get how many alive cells we get. We use a reduction for that, calling MPI reduce. And at the end, we just dump the data, right? The way that I chose to do this is that every process dumps its local grid. And then I've written a little Python script to combine that data and do a single plot, right? So before we move on, what I want to do is I want to show you the result. Here we go. I'm going to show it in Telegram because it loops, right? So what we have here is we have initialized. So this is running with 4 MPI processes, right? And I have initialized the game of life with the thing which is called a glider, right? The glider is the structure that moves along the grid in a diagonal way, right? And remember, because I have 4 processes, each of the processes has initialized its local grid with the glider, right? So this is why we're seeing 4 copies of the glider here. So this is useful to see where the grid partitions are, right? So we have a partition here, a partition here, and a partition here. The 4 different pieces of the grid are spread across the processes. And I have also implemented, as you can see, periodic boundary conditions, right? Which means that when a glider reaches the bottom, it spawns again at the top, right? Okay. So I think there's a lot more that we can say and look at MPI. But the thing I want you guys to remember is this is a distributed memory parallelism scheme, right? It works by sending and receiving messages to other processes. And you have blocking and no blocking, sends and receives. If you use blocking, sends and receives, you can deadlock, right? You run the risk of sending a send, but nobody is there to receive it. If you use non-blocking communication, you need to wait all at the end, right, to synchronize the message passing, right? Now let's see. I think this is basically what you should probably remember. Do you have any questions? All right. Are you ready for a quiz? Yes.
Are these like what's in Discord?
They are not in the Discord, but they are in the class material, right? So right there down here, OpenMP and MPI, right? And the slides contain a code, a link to the GitHub repository where we put the code examples, right? So you guys can play around, and I've added some instructions in the README file, right? Okay, are you ready for a quiz? All right. Are you guys there in the bottom part of this class or?
No, we have thermal recitation now.
Okay, just to know if you get a quiz or not. Oh. Oh, how does he? So I gave you a bubble sheet and quiz.
I thought you were gonna be quizzing, it's like, what?
No, it's just so, yeah, I don't know, how many out the pairs, right? So bubble sheet and quiz at the same time. So.